In this video, we're going to estimate area under the curve using finite Riemann sums. So we're gonna, first of all, let's look at this problem where we have the area, where we have the graph of a function that looks like this. How can we estimate the area under this graph? Area between the x-axis and this graph, I can split the curve, split the graph into a rectangle, a square, a trapezoid, another rectangle, and 1/4 of a circle. Add all those areas and I would be able to estimate the area under the graph for this curve. But what if I have only curves? I don't have any straight lines. My graph is not made up of straight lines. I can divide the region into rectangles and then find the area from there. Estimate the area under the curve using the area of those rectangles. So I can use the left Riemann sum. In the left Riemann sum, we would be using the left-handed height when we find the area of rectangle. In the right Riemann sum, we would be using the right-handed height when finding area of each rectangle. And you can see if your function is increasing, the left Riemann sum will be underestimate because you are losing some area if you do the left Riemann sum. If your function is increasing and you use the right Riemann sum, you are going to be overestimating because you are gaining some area which is not really a part of the area under the curve. So how do we get the better estimation? How do we get the better approximation? What we would eventually end up doing is we would divide the region into infinite number of rectangles. As you can see, the more the number of rectangles, better approximation you will get. More the number of rectangles, better approximation we get. So we can express the area under the curve as a definite integral or limit of the Riemann sum, limit n goes to infinity, means infinite rectangles we have, summation I equals 1 to n, f of xi, this is the height of each rectangle, and delta x is the width of each rectangle. And the width doesn't even have to be same for these rectangles. So Riemann sum is an approximation of area of a region bounded by a function and x-axis. We can approximate the area by breaking the space into more manageable geometric shapes, usually rectangles and trapezoids, and adding their areas. So here again, if this is my curve and I'm looking at the left-handed sum, we need to be careful. So if you see estimate the area using R6, that means it's saying use right-handed sum with 6 rectangles. L5 means left-handed sum, 5 rectangles. M4 means 4 rectangles and using the midpoint. So when we use the left-handed sum, my heights that I will be using will be the left-handed heights. For the left-hand sum, these are the heights that will be used. For the right-handed sum, the heights that will be used will be the right side heights for each rectangle. For the midpoint sum, M4, each of these, actually this was R4 because we have 4 rectangles, so that was just an example. R4, L4, and the next one is M4. 4 rectangles, in this case the height will be used from the midpoint of each rectangle. Height will be used at the midpoint of each rectangle. So we're going to be using the midpoint height for each rectangle, whatever is height at the midpoint. Here's a graph of y is equal to x squared. We can use the left-handed sum or the right-handed sum here to estimate the area under the curve, and it's a parabolic curve. There's no geometric, we don't have straight lines here, so we're not able to estimate without using the Riemann sums. We don't have any triangles, squares, or any 1/4 of the circles like we saw in the first graph. So here we look at the first picture here. We're given a graph f of x, and we estimating the area using the Riemann sums, using the rectangles. So in the first picture, I have only 1, 2, 3, 4 rectangles, and I can see I am losing a lot of area here and a lot of area here. So it's not going to be a very good approximation. The next picture, I use more rectangles, and I'm only using a little bit area here, and I'm gaining a little bit here, but this is going to be a better approximation. In the next picture, green rectangles, I have even more rectangles, and my approximation will be even better because I am just losing a little bit area here and gaining a little bit here as compared to the first picture. And the next one, we have even more rectangles, and that's going to be a really, really good approximation. My area will be really close to the actual area under the curve. So if you use more and more rectangles, your approximation is better and better. Eventually, we're going to say that we want to use infinite rectangles. So we will take the limit as n goes to infinity, and n will be the number of rectangles we're using. So we want to estimate using the infinite rectangles. We often talk about signed area, where area is positive between the x-axis and the function, and the area below the x-axis would be considered negative area. So area above the x-axis is positive, area below the x-axis is negative. I'm going to look at left, right, and midpoint Reimann sums in sigma notation. Sigma is just the sum. So for the left-handed sum, we would be using the left-handed heights. The right-handed sum, we would be using the right-handed heights. Midpoint sum, we would be using the midpoint heights. We will talk more about this when we take the limit as n goes to infinity. For now, let's look at the example. So here we're given a curve f of x equals 20 minus 3x over 2 to 4. Compute R6, L6, then figure out the area using geometry. So this is example to show that this example is for us to see. Now, when you use more number of rectangles, your approximation will be better and better. I'm going to go ahead and draw the curve really quick. 20 minus 3x is going to be a line with the negative slope. So we're only looking from 2 to 4. And it's going to be something like this. That's just my rough estimate. And I want to use R6 and L6. That means I want to divide this into 6 rectangles. We want to divide it into 6 rectangles. So right-handed Reimann sum. So to find the R6, let's go ahead and divide it into 6 rectangles. We have 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. So here we have 6 rectangles here. We divided our region into 6 rectangles. What's going to be the width of each rectangle? Which is going to be the same for both. Width of each rectangle, width delta x, would be 4 minus 2 over 6, which is 2 over 6, and that's 1/3. So that means for the right-handed sum, or before we even talk about right-handed sum, what are going to be my interval points? So my interval points, I'm starting at 2. The next point here, this point, would be 2 plus 1/3. And the next one, this is 2 plus 1/3. 2 plus 1/3 plus 1/3, and so on. 2 plus 1/3 would be 7/3. And 7/3 plus 1/3 will be 8/3. 8/3 plus 1/3 would be 3. This is going to be 9/3. And then we would have 10/3 plus 1/3 will be 11/3. 11/3 plus 1/3 will be 12/3, which is going to be 4. So this is going to be my increments on the bottom. Each is going by, I'm using the rectangles. They all have the same width, 1/3. Okay. So for the R6, keep in mind we talked about you only use the right-handed heights. For the R6, I'm going to be using this height, this height, this height, this height, this height, and this height. I will not be using f of 2, the height at point when x is 2. I will not be using that height. So to find the area of these triangles, I'm going to add all the areas of these rectangles. To find the area under the curve, I'm going to add all these areas add the areas of rectangles, and then that would be my estimation. That would be my R6, sum of the 6 rectangles. Okay, so for each rectangle, the width is 1/3. The height is what's changing. So we're going to find out those heights. Remember, we just talked about for the right-handed sum, we would be using the heights at these points only. We wouldn't be using the first height. Okay, so f of 7/3 plus f of 8/3 plus f of 3 plus f of 10/3 plus f of 11/3 plus f of 4. Okay, so that's length times width for each rectangle, because we already factored out the width, which is 1/3 for each rectangle. So it's length times width. F of 7/3 means the height at that point. F is the y value. F of 7/3 is the y value at point 7/3. So let's go ahead and find these y values now. That's going to be 1/3. F of 7/3 would be 20 minus 3 times 7/3, which is 20 minus 7. That is going to be 13. F of 8/3 would be 20 minus, so I'm going to be plugging the x values into the given function that's given to us in the beginning to estimate. So plugging over here, plug 8/3 for x, 20 minus 3 times 8/3, that would be 12. And the next one would be when I do 3/3, 20 minus 3 times 3 is 9. That's going to be 11. And so on. I'm going to have a 10 and 9 and 8. So that turns out to be 1/3. 13 plus 12 plus 11 plus 10 plus 9 plus 8 is equal to, that would be equal to, divided by 3, it's going to equal 21. So that's our estimation. We are estimating the area under the curve is approximately 21. Now, what if we want to find out L6? For the L6, we have talked about earlier that we would be only using the heights that are the left-handed heights. So I'm going to be using this height, this height, this height, this height, this height, this height, and I will not be using the height at point 4. So for the L6, it's going to be L1 plus L2, the area of each rectangle that we have divided our region into, and I'll add all those areas. So 1/3 times f of the very first height, we're going to use the height at point 2, and then the height at point 7/3, then height at point 8/3, height at point 9, height at point 10/3, plus height at point 11/3. Okay, we wouldn't be using the very last height for the left-handed sums. So I'm using the heights, the left-handed heights in this case. So we already found F2. We're going to plug the 2 as x into the function that's given to us. Let's go ahead and plug x as 2. That would be 20 minus 3 times 2, which is 14. Plus f of 7/3 we found was 13 plus 12 plus 11 plus 10 plus 9. And when you add them all and divide with the 3, that turns out to be 23. Okay, so our left-hand approximation is 23, the right-handed approximation is 21. Now let's see what's the actual area. Because this is a shape made with the straight lines, we can find the actual area here. It looks like it's a trapezoid. That looks trapezoid, something like this. X is 2 here, 4 here. So what's going to be the area of trapezoid? Area of trapezoid is 1/2 sum of the parallel sides times the height, which is 1/2. The parallel sides are here and here. These are the parallel sides. So sum of the parallel sides times the height. So f of 2 plus f of 4 times the height. The height is going to be the right straight perpendicular distance between 2 to 4, which is going to be 2. So 2 and 2 cancels. F of 2 plus f of 4. F of 2 is 20 minus 6, which is 20 minus 6. 20 minus 6 is 14. Plus f of 4 is 20 minus 12, which is 8. 14 plus 8. 14 plus 8 is equal to 22. So the actual area is 22, and we got pretty good approximation in this case. And we see this was a decreasing function. So we earlier talked about we are going to be losing when we use we're going to be either gaining some area or losing some area depending on which rectangles to be used. And I didn't really bother to draw the rectangles because I know the process of finding the area, but we could have drawn the rectangles here, divide our region into rectangles. Okay, let's see another example, midpoint sum. So here we want to estimate the area using 4 rectangles and midpoint sum. So we want to find out M4 in this case. F of x is equal to 1 to 2 and f of x equals 1 over x. So we want to find out 1 over x looks something like this, between 1 to 2. So this is where 1 is and that's where 2 is. Okay, 1 to 2. We're going to divide it into 4 rectangles. So 1, 2, 3, 4. 4 rectangles. Now we want to find M4. That means we want to use the midpoint as the height of the rectangles. We want to use the midpoint as the height of the rectangles. First of all, what's going to be the width of each rectangle? Delta x. That's going to be, this is AB. That's going to be always B minus A divided by N. How many rectangles? So B minus A divided by N. That is equal to delta x. So delta x equals 2 minus 1 over N is we want to divide into 4, so that's going to be 1/4. So I'm going to have my first point is 1, and the next point will be 1 plus 1/4, which is going to be 5/4. And the next one is 5/4 plus 1/4, which is 6/4, and we can write it as 3/2. 6/4 is same thing as 3/2, plus 1/4 is 7/4, plus 1/4 is 8/4, which is equal to 2. So these are going to be my increments. So this point is 5/4, this point is 3/2, and this point is 7/4. Okay, so when we estimate the area using midpoint, we will be using the height at the midpoint of the rectangles. So I need to find exactly, I'm going to be using these pink heights which are on the midpoint. So I need to find the midpoint of each of these interval. What is the midpoint of each of these? So midpoint of 1 and 5/4, to find the midpoint, we will do 1 plus 5/4 divided by 2, which is going to be 9/8. That's the midpoint. That's the first midpoint. The next midpoint would be for 5/4 and 3/2. So add them up and divide by 2. 5/4 plus 3/2 divided by 2. That would be 11/8. 11/8. And the next we have 3/2 plus 7/4 divided by 2. That would be 13/8. And then 7/4 plus 2 divided by 2, that would be 15/8. So we found all the heights in the middle here. We didn't find all the heights in the middle, but we found the x values in the middle. We found the x values in the middle, where the heights I need to calculate for the area. So M4 is going to be the area of first rectangle, area of second rectangle, area of third rectangle, and area of fourth rectangle. What's the width of each rectangle? The width of each rectangle we calculated earlier is 1/4. And now we're going to multiply with height of each rectangle. We're going to be looking height at x equals 9/8, x equals 11/8, x equals 13/8, and x equals f of x equals 15/8. Okay, so 1/4, f of 9/8. We're going to plug x as 9/8 into the original function. That would be 8/9, because it's just 1/x. The y value is 1/x. 8/9, and that would be 8/11. 8/11 plus 8/13 plus 8/15. Now go ahead and add these using a calculator and estimate the sum. That would be our estimate using the midpoint in this case. That would be our estimate using the midpoint for midpoint sum. That's all for this video. We saw a left-handed sum, right-handed sum, and the midpoint sum, all using the finite rectangles, finite number of rectangles. In the next video, we're going to take it to infinite rectangles. We're going to write the definition of definite integral and then take the number of rectangles to infinity. We'll say the limit n goes to infinity.